Welcome to our next video for Ch14. In this video, we're going to begin talking about transformations in the context of linear modeling. So there's really two categories of transformations that we can do. One is a transformation on one of our predictor variables. One is a transformation on the actual response variable. So the reason that we consider transforming a variable in our model is when we might have an assumption violation otherwise. So as a reminder, when we're doing linear modeling, which is usually the most common approach to modeling, it's usually the one that's the most versatile and also the one that's easiest to interpret. There's different assumptions that need to be true in order for that model's methods to work. In other words, when we do inference on a parameter, or we do inference on the response given a particular set of x values, we're assuming some certain things to be true. We're also assuming that the model itself is actually linear and that we're actually fitting this appropriately. So as a reminder, our class kind of divides this into four categories of assumptions, and I will go over here for a second. The first is that residuals are independent. So an assumption violation, I guess these are written as assumption violations. The assumption violation then would be that our residuals are not independent. And what we mean by that is there's some kind of a pattern into how we selected the observations. So I think in a previous video I mentioned like two different ways this is often not true. One is if you really have a hierarchical linear model where you have a couple sources contributing multiple observations each to my data, in which case I should probably do HLM, which is hierarchical linear modeling. The other case, another common case, would be time series, where my observations are actually kind of linked sequentially. And you usually notice that when you see some kind of like clear pattern where this observation is directly related to the observation that came before, in which case time series modeling would probably be the most appropriate thing. And those are usually, this independence violation is usually going to be obvious from the context of where we're getting our data. Sometimes we can kind of see it in the data itself, but really it's the context that helps us know if that's going to be a problem. So if the residuals are not independent, we really shouldn't be doing a linear model exactly as we're doing here. Relationship between predictor and response is not linear. So this is obvious, but if we're going to fit a linear term between a predictor and response, then it makes sense only if the relationship itself is linear and not something else. And this would be an example where a predictor transformation would make a lot of sense. So as we're going to talk about, we might use a polynomial term or a natural log of the predictor or something like that as a way to change the representation of the predictor such that that transformed predictor and the response now have a linear relationship. And we'll also talk about this whole wait a second moment. That doesn't seem linear anymore. Like I'm literally changing the predictor and calling it linear when it's not. So we'll talk about how the wording works around these ideas. And then the third and fourth idea kind of go together, and that's when the residuals are either not normally distributed or don't have a constant variance. And usually that's addressed with a response variable transformation. It's not going to necessarily depend on just one predictor in your model. It could, but often these can be addressed by a response variable transformation that now makes the representation have normally distributed constant variance residuals. So those we'll talk about in the next video. In this video, we're going to focus on predictor transformations and this idea of what do we do if the relationship itself isn't linear. I can't just fit a linear term. It would be a bad fit. So here's kind of a starting point of, hold on a second, what exactly is a linear model? Because if we're talking about fitting, say, a polynomial term here, so right here is an equation, a model equation, where I have added x squared into this model. This would be a quadratic equation. So that's not a linear model, is it? And the answer is actually yes. As we define linear modeling in statistics, it's not that the relationships themselves are always linear, but that I have what's called a linear combination of predictor and parameter values fitting y. So even though this itself, even though the predictor itself does not have a linear relationship, this is what's called a linear combination. And a linear combination means that I can additively put together these terms where I have a parameter times some expression of a predictor, and I can just add them together. Whenever that's true, we can call it a linear model, even if the model itself looks like this. And that is, I know, a really strange idea, and I know you're sitting there thinking, this is not linear. Why are we calling this a linear model? And again, it just kind of comes to notation and statistics, that we use this term linear model not when the relationships themselves are linear, but when the equation can be written as a linear combination of terms. Because if you want to think of it this way, this x squared is now like a new variable. We could just call this z, right? So I could also just call this y equals beta naught plus beta 1 x1, whoops, plus beta 2 z1. Or let's see, yeah. Or it would just be x2 or z. Yeah, that honestly, that works too. I'm trying to think. So that the x1 is to mean that we could have multiple x's, like x2, x3. So either way, it's fine. But right, so if we set z to be equal to x squared, then I could just write an equation like this, and this is technically a linear model. This is a linear combination of predictors. So it's less to do with what the actual fit is and more to do with how I can write the equation, that I can just kind of redefine a new variable to be equivalent to x squared, and now this is just a linear model. And in terms of how we're building the model and how we kind of work with it, nothing changes. All of these methods that we're talking about and the inference that we're doing still totally works for this situation. So all that to say, linear model just means linear combination of predictors. It can be written in a format that looks like this, and everything that we know works as we would expect. So then that kind of brings into the question, what is a nonlinear model? And these are things that we don't use very often. There are situations where people might fit a nonlinear model, meaning that they can't fit the model in terms of a linear combination of predictor expressions. And so here are some examples. One would be a power function, one would be a Weibull growth function, and one would be a Fourier function. So all of these are examples that fit very, very complex functions. And so they can be appropriate in certain situations, but none of these can be written as a linear combination of predictors because of how the parameter, so these, whenever you see this like theta, whenever you see like this theta 1, I can't, okay, there we go. This is kind of like our betas. I just screenshotted an example on another page, so that's why it's written as theta instead of beta. But these thetas are like the parameters, and then x kind of represents like possible predictors that I might be using. And so the way these expressions are written cannot be rewritten as a linear combination of predictors anymore. So this is a situation that we don't really care about in our class. So this is kind of like a big X. We're not going to be dealing with nonlinear modeling at all in this course. And again, it's a relatively rare thing to do. There's not a whole lot of situations where you need to do this. Instead, we're going to be focusing on situations where we can write the equation as a linear combination of predictors. All right, so again, when to use a transform predictor, I'll go ahead and move back over here at this point. So we typically do this whenever we see some curvature in the relationship between a single predictor and the response variable. It's not going to make sense for me to try to fit just a straight line here, but instead I need some kind of curved formula, some curved representation between the predictor and the response. So this example on the left would be a situation where a polynomial term would help a lot. The situation on the right would be a situation where it's actually a logarithm that would work really well. So finding an expression for the predictor that helps model the response variable appropriately. Some of it just kind of depends on experience and knowing what different relationships look like. And some of it's just a little bit of trial and error. But these would be cases where I don't really have any other assumption violations other than the fact that it's just not linear, right? I don't have non-constant variance. I don't really have any reason to say that the residuals are non-normally distributed, at least not yet until I fit this new model. So it makes sense to just do a predictor transformation in both of these cases where there's no other residual concerns other than just the linear association part. So again, this is kind of a little bit of trial and error, that I can start with a linear model, I should say a simple linear model, a simple linear expression right here. And so I can see that that is represented with, I believe it's this green line right here. And this green line's not a great fit for this data. It's better than nothing, but it's still not quite doing what the data is doing. So it makes a lot of sense to go ahead and add a polynomial term. And we're going to start with the second order polynomial. And that's going to be represented by this blue line right here, which does seem to be doing a little bit better. But it does still seem like we could do better than that because there is a little bit of a change in direction here. So we see this right here, but then we might be a change in direction right about here. It's kind of hard to know for sure without more data, but we can certainly try a third order polynomial as well. And we see that this red line fits data really well. So maybe that's really the relationship that we're seeing here is a third order polynomial. Now, just a heads up, even though we are fitting polynomials of higher order, like we still obviously have the lower order terms as well. So depending on how comfortable you are with functions, and I guess this would be either maybe like Algebra 2 or pre-calculus, you might have, or honestly before that, you probably learned about how the different elements of a polynomial affect the graph differently. So we still need these lower order polynomials as well, even though we are going up to this higher third order. So go ahead and include them all in that model when we fit it. So if we're coding this kind of a transformation, let's say that we're building a model where we want a second or a third order polynomial. We could just write that in the linear model function here, but take notice here that we have to use what's called the I function, which stands for inhibit, in order for R to understand that we're fitting this as a predictor and that we're not literally just trying to square all the values of MPH here. So rather, we're trying to understand this as a predictor variable, and inhibit will help us do that in the actual linear model code itself. So just kind of keep that in mind there. So if we create this model and run a summary, you'll see that we have, again, our intercept term, the first order term, so just MPH by itself, as well as second order and third order term as well. And these are, again, are going to be our beta estimates for those terms. So if I were to write this equation out, this kind of this fitted equation based on this form, and based on this being kind of our best estimate for these parameters, then I have y equals 2.258 plus 1.291 times, I'll just call it x, minus 1.502. Actually, that's to the negative 2, so let me switch that. It's going to be negative, 0.001502 times x squared plus 4. That's much smaller actually. Plus 0.0000466 times x cubed plus an error term for each individual response observation. So we can kind of see how this gets translated. These are our beta coefficients, or at least our beta hat coefficients for each term in the model. And this seems to be a relatively good fit. We can also look at the R squared values. So we will talk more about adjusted R squared in a future chapter, but I'll just kind of mention it while we're here. Every time we add another term, whether it be another predictor or just another polynomial term, we are going to have a small penalty show up in what's called adjusted R squared. Whereas R squared represents just the actual variance being explained, with these predictors and these terms with this particular set of data. But the thing is, we can add bad predictors, we can add bad terms, and r squared isn't going to tell us that because r squared can't get any lower. It's only going to get higher as we add terms. So adjusted r squared will actually go down a little bit if you add a bad term, or if you add a term that isn't adding anything more than random chance variation. So we'll talk more about that in chapter 16 when we get to model selection and variable selection. But for now, I'll just kind of mention this, that r squared is one thing you can kind of look at to compare models. The other option that we've seen before, oops, I'm getting ahead of myself, is just doing a direct Ftest between two candidate models. So as we'll see kind of on, I think it's the last slide, if we're comparing, say, a third order polynomial expression to a second order polynomial expression, I can fit both models and then run an ANOVA, which is going to do an Ftest between the two models to see if I'm making any statistically significant progress by adding the more complex model. But we'll see that again in just a second here. So just again, some caution about complexity. So we can keep adding polynomial terms, or we can keep transforming and adding more complicated expressions of the predictor. But we want to be cognizant of interpretability, which is really important when we're doing explanation modeling. So in some cases, you might remember we talked about prediction versus explanation as kind of two goals that we might have in modeling. We might have one goal more than the other. Usually both goals are important. I don't think there's a whole lot of cases where we care 100% about one and 0% about the other, but there's certainly cases where we care a lot more about prediction and cases where we care a lot more about explanation. So if we care a lot about explanation, we want to be careful about creating really complex models because it makes it a lot harder to understand what that relationship is. The other thing, and this is cognizant, or not cognizant, but certainly in the picture for both of these, is that overfitting is just a concern in general. That if we keep fitting more and more complex models, especially if we don't have a whole lot of data to work with, we're going to begin to model the noise instead of the signal. We're going to start kind of going after individual observations rather than the overall trend of the data. And so one way that you can kind of guard against overfitting is to kind of hold some data separate as test data, fit the model with your training data, and then try your model on with this test data to see if it still makes sense. Because if you start overfitting, you're going to see your explanation power drop quite a bit on the test data. So I just kind of mentioned this, is that second and third order polynomials are still relatively sensible and interpretable, but always be cautious going too much farther than that. We can add fourth and fifth and sixth degree polynomials if appropriate, but we only want to do so if it still makes sense. And probably, at that point, we probably care more about prediction because explanation is going to be a lot more confusing if we're adding a lot of complex terms. So all that to say, it's not that this is never relevant. It's not that there's never actually a fifth or sixth order relationship, but that it's easy to just start overfitting if we're totally concerned with, say, r squared going up and not concerned with, does this just make sense? All right. So determining appropriateness, this is what I was mentioning before. If we're trying to decide if we've gone too far, if it's really necessary to go this extra step, we can do an Ftest to compare two models using the ANOVA function. So this is different than AOV. AOV would be for just running in it, like creating an ANOVA model with the response variable and some predictors. ANOVA is to directly compare two already created models to see if the variability being explained by the more complex model is statistically significant in comparison to the variability explained by the simpler model. So we can do this here with this data. So here's some data where it's kind of hard to tell, like, is this a, I don't think it's just a quadratic relationship because I think we would see the dots go down a lot steeper on either side. So it does make sense that it's probably at least a fourth degree polynomial, but is it possibly a sixth degree polynomial that we're seeing here? And so we can fit both of these models, run the ANOVA, and then we can see the Ftest result with the p-value of about 8.4%. So that kind of tells us this is kind of a borderline case where maybe we are getting some ground, getting some ground by fitting the 6-degree polynomial, but it's not like overwhelming evidence. Quite honestly, we just probably need more data to know for sure if that makes sense. But this would be one way that we can kind of test that. Obviously, if we get a fairly high p-value that's saying, hey, this is probably not adding anything by adding these extra polynomial or transformation terms. If the p-value is really low, it's saying that we are making some progress in comparison to the simpler model that we have as well. So this can be a good measure for deciding if you should go more complex or not.